Hey everyone, I am Saheb Kumar and welcome to PrepTrain in another video of Break the Tech series. It feels really good to be back finally after 8 months. I want to sincerely apologize to the audience for the delay. I was going through some personal issues and I had to take a step back for a while, but now everything is finally sorted and I'm really glad to be back to continue our Break the Tech series. Thank you so much for sticking around and watching my videos. For today's video, we are going to dive into one of the most interesting research paper when it comes to understanding large-scale distributed databases, the Amazon DynamoDB paper, which they mention, the AWS team mention it as a scalable, predictably performant, and fully managed NoSQL database service. And honestly, if you have ever studied DynamoDB only through documentation, architecture diagrams, or a couple of system design videos, you are probably familiar with what DynamoDB does. But this paper gives you something much more important and valuable, an understanding basically of why the system has been designed the way it is currently working, and what problems did Amazon faced when they tried to operate this entire the system, the distributed database system at a massive scale, and basically how the entire architecture has evolved over years. I have already went through this entire research paper and it's a must read if you are really into tech. So what makes this paper really interesting to me is that DynamoDB is not just a system that was designed just once and had been left untouched. It has been running at enormous scale for years now, and the most interesting thing is that the engineering that are operating it have continuously, solve new problems around scalability or performance or operational complexity. But in a way, we can say this paper is not just about DynamoDB. It is about what happens when a distributed system becomes so critical and so large that even small, ineffective, problems can become massive problems. And that is exactly what I want to explore in this video. We are going to go through the entire research paper slide by slide, understand the important design problems that Amazon faced. We are going to break them down and then find out what was Amazon actually trying to solve, and most importantly connect those decisions back to the fundamental concepts of distributed systems. So whether you are just preparing for system design interviews, working with distributed database, or simply trying to understand how systems like DynamoDB actually evolve at Amazon scale, I think there is a lot to learn from this paper. Alright, let's get started with another video of Break the Tech series and dissect this Amazon DynamoDB research paper. All right, so let's start with the paper first. The paper first start with the abstract section on page 1, and then it talks about the first line itself, that Amazon DynamoDB is a NoSQL cloud database service that provides consistent performance at any scale. There are so many interesting things in this one single line that I will tell you. So basically, let me give you a brief overview. So Amazon DynamoDB is basically a fully managed NoSQL database. Good enough. You might be knowing about what NoSQL database are, so I will not go to there. I will just skip. You need to talk to it via API. So you do not provision any storage nodes, or let's say you don't need to patch any cluster, or let's say invent some kind of how to debug this or how to debug that. Everything is being managed by AWS directly. The research paper is from 2022, I guess, of some tech conference, and these papers have been written by those engineers who run this service in actual production. So the claim here by AWS is that at any scale, their system is highly performant and consistent. And with regards to that, they have given this fact that in Prime Day 2021, which ran for, let's say, 66 hours something, they have mentioned, the peak request was around 89.2 million request per second, which is itself is crazy. And then they said ki they were able to serve all of these trillions of API calls made by, let's say, Alexa, Amazon.com, or different services within Amazon with high availability and single digit millisecond response and latency. Now, the P99 basically is supposed to stay in this band basically as the table grows from megabytes to terabytes. So they are saying that it does not matter how much is the size of the table, our P99, we will try you to give a consistent sub-millisecond performance at any scale. And this claim itself is really crazy. So it will be really interesting when you will go and deep dive into this research paper again, at how they have built this entire system. We will talk about it in detail. In this research paper, Amazon also claimed that there are hundreds and thousands of internal customer as well as the external customers who are currently using this, and this DynamoDB is actually powering the AWS Lambda, or let's say the related services. And regarding this, they have also said that their service level agreement, or what we call as SLA, is basically 99.9% for regional deployments, whereas for global deployments it can go up to 99.999, so 5 nines, which is again crazy. I will talk about this in more detail. How are they ensuring that this is happening? Because see, in distributed system, what happens when you claim that a service is working at this particular SLA, so all the system services should work at a better performance than that. So we will talk about this in the research paper. How did they ensure that this is happening over there? One interesting thing that Amazon says in this research paper itself is that DynamoDB has evolved over years, and they have mentioned this in the research paper also, saying few things like how Dynamo paper came first in 2007. We will explain this in detail again. Then SimpleDB came. Then eventually both services were like, features from both things were taken, and DynamoDB was launched. And then eventually within the next 10 years, how many different new features of global tables, on demand, and prime day, and everything, like they have been talking about in the 2022 paper. They have been talking about this, that over the next or last 10 years, how many features have they added, and they have to ensure that there is no downtime at all during any of the deployments. So how did they handle it? It's crazy. But before going into the technical detail, I would like to discuss one more thing. While going through this entire research paper, I came across multiple terms which were really, really, really interesting. And I have highlighted them like in my research paper, but I ensure that I put them here as well. So these terms that you are seeing on the slide are basically those terms which are spread across the research paper. And I thought that these are the some of the terms that might interest you. If you don't know about them, or you want to deep dive further to understand distributed systems more in a better way, you can look into these things. If you know some of them, good enough. If you don't know one or two, three, you can look into them further if you want to deep dive again. All right, let's continue. Let's talk about the 6 core properties of DynamoDB, which helps us understand the system in a better way. So the first core property is basically fully managed. Basically, what do you mean by fully managed? So basically, DynamoDB is designed so that the whatever team at my company, the SRE, is not responsible for running the database fleet. Everything will be managed by AWS itself. You just need to create the table, the read and write items through the service API. So you will call the API, the data will be inserted, and whatever you want to do with the table. But apart from that, you don't need to maintain the infrastructure for that table at all. Everything will be managed by AWS. So basically, Amazon Web Services handles the entire scaling, patching, or let's say the fleet management. So let's talk about the second core property, which is multi-tenancy. So what happens that if many customer can share the same machine without one workload, impacting the other, we can reduce the cost for giving separate machine to separate customers. So DynamoDB stores data from different customers on the same machine. So in simple terms, basically what I want you to understand is, so let's say there is a machine or DB machine basically. Now AWS has assigned this machine to multiple customers. Let's say C1, C2, C3. Likewise, a big chunk has been allotted to C4, and likewise there is C5 as well. And all of these customers are using the same physical host, and this is helping them to utilize the machine in a better way, because different loads can keep coming for different customer, but they will ensure that no one is getting impacted due to the other one. And these cost saving basically help them to pass it to the customer, and this way the performance is also increased as well as the cost is low. uh, and this is basically like a resource isolation problem at the scale of a shared storage fleet. The third core property talks about the boundless scale of DynamoDB, which is basically once the operational burden is off from the application, the next question which comes is whether or not the table can grow as much as we want. So basically, there is no predefined limit on how much data a table can store, how much throughput it can take, or let's say how many items it can hold. So table grow elastically, and what happens is that the service is designed in such a way that it will move a table from a handful of server. So let's say there were 3 servers initially, and they were holding the table. So let's say T1, T2, and T3. Now, if the size of the table grows, what will eventually happen is that this table can be stored across thousands of other servers by breaking it down further and further and further, and your throughput and storage will never be the issue at all. Let's talk about the next core property, which is basically predictability or performance. If you remember, I said this word in the first line of the research paper also. What do you mean by predictable? So scale by itself is not enough, right? So a system that can absorb enormous throughput and still it will feel broken if, let's say, a small fraction of request becomes extremely slow. So predictable performance, what it means is about controlling the latency. It also means controlling the latency basically, and especially at the tail end. So if there is P99 we are talking about, we will ensure that the P99 should be under 10 milliseconds. And this means even the slowest percentage of requests are supposed to stay within their band at any load. And the get item and the put item APIs that DynamoDB offers, they are really small. So basically the service can answer with consistent low latency. Let's talk about the next core property, which is basically uh, high availability. So high availability basically, of course, means if you are having a database, you would need that even if it is a managed, basically shared, basically, and then it's a scalable store, right? So still it has to survive the machine failures. This keeps happening in distributed systems, right? So DynamoDB replicates data across multiple availability zone. If you know about the concept of AGs, the availability zones, and there are globally distributed AGs. So the world is divided into, let's say, 30 or 40 plus AGs, and so the same data can be replicated on multiple AGs depending upon how you have configured it. And then customer can also create global tables which are basically geo-replicated across several connected, selected regions. So the availability service level agreement that I was talking about, the SLA, is 99.99% for regional. So if you are storing it within your region, there are 99.99% chance that the data will be never lost. And in case of global, there is 99.999% chance that the data will be always there. And this is the service level agreement that DynamoDB will not break. Let's talk about the next core property, which is flexible. So this flexibility is something which is like little bit interesting to understand, because in DynamoDB, the tables have no fixed schema at all. So each item can hold any number of attributes, and you can treat the table as, let's say, key value or as documents. So on a read, what actually happens is that the caller basically chooses, let's say, they want strong consistency or they want weak consistency. If you know about consistency, or you don't, I don't know. So basically strong consistency means you will be always given the latest and the fresh data. But in eventual consistency, this means okay, the data might be a bit old or stale, but still it's somehow the latest, but we cannot guarantee it's the latest, right? So it totally depends on your use case. So let's say in case of, let's say, Instagram likes, it does not matter if it is 413 or 414. So even if it is a bit stale, it works. But there are cases when we want strong consistency. Let's say banking transactions, they often need strong consistency. We cannot be like, no, your money is like this much or it might be this much. So there we need strong consistency, right? So the DynamoDB service also supports atomic transactions and update streams. And the atomic transactions on a NoSQL database is such a crazy concept. You should read about it further, that how do they ensure that this is happening. And it's really crazy. It's in the research paper as well. So the six core properties that I talked about are basically coupled. So managing the entire fleets, it makes multi-tenant scales practical. Isolation keeps one customer from impacting the other customer and become a noisy neighbor. If you have read about the noisy neighbor problem, which is a very famous problem in distributed system. So noisy neighbor is like there are two systems which are kept together, and due to one, the other is getting impacted. Although they are separate, but it just there is huge load on one system. So how did Amazon DynamoDB ensure that noisy neighbor problem does not come? We will talk about it again in the later slides. Now that we have discussed all the six core properties of DynamoDB mentioned in this paper, let's talk about the history and the journey of DynamoDB, which is accordingly interesting. So, the six properties we talked about did not just come out of nowhere. So, the first ancestor of DynamoDB was actually Dynamo. Dynamo was built for shopping cart data. So features like consistent hashing or vector clocks or the gossip protocols, all of these things were available over there. But the problem was it was single tenant and internal to Amazon. So team used to run their own installments of Dynamo, and it was an operational issue because every team now needs to understand how it works, how to manage it, how to expand it, and all. So that operational cost basically it became a barrier to its adoption. Uh, then after some time, Amazon launched SimpleDB. SimpleDB was basically a fully managed database as a service. It had very simple APIs for interaction, but again there were some limitations. So it had a 10 GB limit on the max table size. It had eventual consistency only, and also there were some unpredictable latency, due to which, although people were not happy with it, but they were very happy with the fact that they don't need to manage this particular DB. So this DB I think came around 2000 against the 2008 bit, somewhere around 2012 simple DB came. Because of also this 10 GB limit on every table, what developers used to do was they used to split the data across tables to work around it, because of course you don't need to manage the table. But again, it was bothersome. So eventually what came was DynamoDB. So DynamoDB was launched as a public service in 2012, and it is basically it is the synthesis of entire good things from Dynamo as well as SimpleDB, the managed operations, consistency, or we can say a table model, which is richer than a pure key value store of Dynamo concept. It basically shares most of the Dynamo's name, but little of Dynamo's architecture. I will explain it further. So after launch, the service kept growing without taking the core properties that we mentioned down. And many new features were later added, like in 2020, PartyQL was added. Likewise, in 2018, transactions have been added. In 2017, global tables were added. So likewise, you can see that the secondary indexes were added in 2013. So the features have been kept adding, and there is this brief description again in the research paper. How did they ensure that their deployment should not break the existing customer experience? So all of these things are there that we will talk about. Every feature was supposed to be backward compatible. So basically, the paper entire framework is evolutionary engineering, and we can say that they need to add the feature and keep it backward compatible. And I have mentioned here, like what they said in the research paper, that every feature that they are trying to create uh, should not change the workload, as well as they were having feature flags to roll it out on a specific region only for testing purpose. And as well as there were automated rollbacks. We will discuss this again in deployment section of the research paper. So let's skip to the next part, which is basically the prime day number that they have given in the research paper that I mentioned earlier as well, that in the prime day sale of 2021, they mentioned that they were getting a peak traffic of 89.2 million per second, and P99 of that was handled within 10 ms. So which is crazy. uh, Overall, over a period of entire year, they are getting trillions of calls, and now it is rolled out to, I think, 30 regions. There are global tables, multi ages replication, as well as it powers many of the internal Amazon sites as well, like amazon.com, Prime Video, Alexa, and many other customers that uses AWS all over the globe. Now that we have discussed the journey of DynamoDB, I think more interesting parts are now coming, which is basically the architecture of DynamoDB. So, in DynamoDB, the unit that you eventually create is just a table, which is a collection of items. Now, an item is a collection of attributes, and applications, basically, whenever they are integrated with DynamoDB, they can create the tables, and they just mention what are the read and write capacity they want, and accordingly entire rest of the thing DynamoDB just handles it. So summarizing the entire discussion, basically applications can create table, put an item into the table, get an item on table, and various other APIs that they are provisioned with, and they can run their operations. And after this, what happens that in the storage layer, the tables can have a collection of attributes that we then send, and different attributes are also allowed. So if you see here, name, orders, email, and preference was mentioned, but in this case, phone was mentioned. So there is no fixed schema, basically no SQL database, right? And inside this, we can have a key value or a document based model as well. So good for storing as much data as we want. And the guarantee of DynamoDB is basically like, let's say if the data is 1 KB item, the average service side latency will be single digit millisecond max. So the table is basically serverless, and eventually everything is being managed by AWS itself. Continuing to this, let's discuss the items in detail. So basically items, just like I said, are schema-less. So only the primary key schema is fixed at the time of creation of the table. Rest of the fields can be like, there can be a name or tier or email. In something it can be phone, and in some cases it can be some other nested user attributes as well. It is totally up to you, right? So let's look further into this. So when we talk about the keys, how does that thing work? So there are concept of primary key, there are partition key, there are sort key, and there are secondary key. There are lots of keys, right? If you have been interested in database knowledge, then you must be knowing most of these things. But if you don't know, so basically primary key is the uniquely identifier. So let's say a user ID. Eventually this partition key is hashed, and then that hashed value is used to decide uh, like where the value will go. So all of these things, so let's say, because every data related to user one will be stored at some place, right? So once we decide that okay, this is the primary key, then accordingly every value associated with a particular primary key will go into one place only. Now there are again partition key. So partition key is basically the same thing that I said. The primary key is hash to generate the partition key, and items with the same primary key, or basically the partition key, stays together. Then there are sort key. So sort key is basically, it orders item within the same primary key also, if there are multiple rows, how will we decide that what should be the sorting order? So sort key decides that order. And then there are secondary keys. So let's say apart from user ID, if we want to filter for, let's say, a email ID or something like that, so we can use the secondary key. So instead of going through all the rows, we can just directly search the table using that particular field directly. Now that we have discussed the keys here, let's go into much more detail into this with the primary index, the local secondary index, as well as the global secondary index. So these concepts are mentioned in the research paper. So what actually happens that there is a concept of scanning, right? So if you want to search for a particular data set, let's say all the transactions of a particular user, or let's say there which user is having email of xyz@gmail.com. So all of these things needs to have indexed so that the search can be faster as compared to just going through all the entries. So what actually happens that the primary index itself is the user ID in our case, right? So primary key is the table itself where we say that, hey, give me all data related to user number 41. Local secondary index is something like within that table. Let's say if a user, let's say in this case user 42, 99 and 17 are there, which are differently unique, right? But if we want the same partition key within that table, then we can use this concept. LSI is basically local to a partition. So basically what happens is the same primary key will be there, but the sort key will be used with the secondary index. So what actually happens that within the same partition, we can use this concept to filter user more faster. So GSI, or basically global secondary index, what there happens, it uses a altogether different primary key. So the email example that we were giving. So you can get that particular item using that key without scanning all the tables. So reads in both for secondary indexes are eventually consistent only. But again, it depends on the caller's choice of the table read, whether they want strong versus eventual consistency. Let's talk about the method that we are allowed to do on the table. So basically in DynamoDB, we can do a put item, a update item, or a delete item, because it's a key value store, something like that, right? If I give you a brief summary, so basically writes are put item, insert or replace comes under the update item, modifying attributes, or let's say removing by a primary key, these things can come under delete item. Any write can carry a condition that it must succeed, and all of those writes will go to the partition leader directly. So the leader basically appends a write ahead log, or we call it WAL. So this write ahead log concept is important, and this write ahead log is appended as a record, and eventually what happens then, it is applied to the B tree inside the log structure tree that they have, and we will eventually come back to this. But the thing is, there is only one writer per partition. So the logs eventually are written by master only, and we will talk about the consensus algorithm, how it works. Now that we have discussed about how write item works, let's talk about how read items work. So basically read splits into 3 operations, and only 2 of them are the actual ones which you want. So get item is basically a point lookup. So what actually happens that you give the full primary key or partition plus sort key, and eventually you will be able to find the item. Then you have query, which is a range scan. So inside this, you just give the partition key, or you can then retrieve all the items that are sharing it. But there is one more operation called as scan. So in this scan, what actually happens that what you do is you don't name any key, and it will walk all the items in the table, and then it will find out the responsible things that needs to be returned, and accordingly you will get the data. Now, interesting thing is that the capacity consumed and the latency that is being receiving from the DynamoDB, it keeps growing with the number of tables that we, or the size of the table data, right? So what actually happens that when you do the scan operation, it has to go through all the tables to find out your answer, and it increases the latency. And that is why you need to avoid it and rather use a secondary index to filter out the data in a better way. One more important thing that you should know is that strongly consistent read will only be served by the leader, whereas eventually consistent data can come from any of the replica that we have over there. All right, now that we have discussed how the data model and API basically works in DynamoDB, let's look at another aspect or the next part of the architecture, which is basically the hash partitioning and how it works. This is also really interesting, and now it starts getting more technical about how the entire hash partitioning works. In hash partitioning, basically the most important thing is the partition key, of course, because that is what decides where the item will go. So this partition key is basically generated by a hashed function, because what actually happens, so let's say the partition key was a user ID. So user 42 is of course not a valid address, right? So for a user table where partition key is user ID, what will happen when the application writes an item for let's say user 42, what will happen that the database cannot treat it like a normal, the raw user ID basically as a machine address. So what will happen? It will need a deterministic mapping from a key partition, or let's say the same key basically should land always in the same place. This mapping eventually requires an internal hash of the primary key, and the paper describe it as a hash function. So let's say MD5, one example that we can say is, so the job for MD5 is to be deterministic, and it should be also roughly uniform. So what actually happens, so let's say the hash function will take user 42 and it will convert it to a hashed value, and then that hashed value is then distributed across the memory, and then partitions are created which are actually contiguous, not continuous. I will explain it further if you have read about arrays, how array works. So the hash output basically together with the sort key, because sort key is also important, that actually determines where the item is stored. So items that share a partition key will always stay together, and they will only coexist when their sort key will differ. Okay, so now let's look at the next thing. So the hash space is basically divided here into partitions, and these are contiguous ranges. So each partition basically owns one of these ranges. The entire range is now broken into contiguous range. Now let's say when user 42 basically hashes into some particular range, let's say P3. So what will happen? The partition P3 will be called, and the partition P3 will be the owner for user 42, and the table will be split in such a way that the partition and the throughput remains stable, and the storage can grow accordingly. So you do not need to search every partition whenever you are looking for a particular data. So what will happen that based on the user key, so like user 42, you can just generate the hash and find out that okay, where this data, in which partition it will be, and you can directly go to that partition, and that will further help you to find out where the data is, what the data is, and accordingly. Now let's look at the next interesting thing, which is what is happening inside the partition. So inside the partition, what is happening, the data sits in a B tree. So this is of course a sorted key value index on the disk, right? So lookup by key are very fast. So durability, of course, we cannot always wait for the B tree. So what happens that on write, the partition manager, what it will do, it will write it into a write ahead log that hey, for this user 42, this operation needs to be done, and this write ahead log is basically append only. So put, update, and delete records, everything is append only. So that log is basically the durability and we say the crash recovery main point or spine. So we can use it for archiving or scrubbing or restoring the data if some crash happens. And all these changes that comes to these write ahead log are then eventually applied to the B tree internally. But what we ensure is whatever change is coming, it should go to the write ahead log. Now, a partition still cannot depend on the machine. So it replicas are placed across the globe in at least 3 availability zones, and they use multi-paxos basically for leader and consensus. I will create a dedicated video on how available like basically multi-paxos or consensus algorithm works in near future. But for now, just understand that there are now 3 replicas stored across the globe. So now there are, even if one server crashes, we will still have data in some other AG. So data lost will be minimized. Now, one more interesting thing that I keep telling you again and again, that only the leader will serve the strongly consistent read or strongly consistent write. So this thing, if you see here, there are 3 replicas, A, B, and C. A is the leader. So if you want a strong, consistent read that give me the exact latest value, only the leader will give you. But if you want just a non-consistent or eventual consistent, basically, what will happen? You can get it from any of the replicas, and that is good enough. But write will be always handled by the leader, and strong read as well. And due to this, what happens that a healthy write quorum, whenever 2 out of 3 replicas confirm that, hey, this is confirmed that I am adding this to my write ahead log, we can say that the data is now persisted, and eventually, even if there is some failure, the other failure node can like cope up. We will discuss this again, what happens in the failure scenario. So now let's look at the next important thing, which is how the partitioning and consensus happen in DynamoDB. So in DynamoDB, a table is not just a very like big store. So it is very small partitions, many partitions, and each is holding a disjoint, contiguous slice of the hash space. So this entire table is now stored in different partitions, and each partition is a contiguous array. There are B trees plus write ahead log in each partition. Now, each partition is an independent unit of storage and throughput. So eventually you need to manage that whatever global scale you have set for your table, like the in terms of throughput, that is being made by every partition as well. We will discuss this again later on, like what blockers came there. Because each partition in DynamoDB is an independent unit of storage and throughput, it has its own replication group, write ahead log. So that independence is what lets the table grow by adding partitions instead of rebuilding the whole dataset. Let's deep dive further into how this actually consensus and partitioning works. So each partition is basically, let's say, node A, node B, and node C. They are copied into 3 storage nodes in 3 availability zones. Now these copies are a replication group, so they run multi-paxos. And now it gives us 3 guarantees that we actually need. So first of all, what guarantee we need is a committed log. Basically, the entry will be never lost, because now there are 3 replication groups. The group, we can survive basically even if one availability zone goes down, still it will be there at least on 2. Now, a healthy write quorum is like 2 out of 3 replicas should confirm that they are accepting this change. Then only we confirm that, yeah, this is confirmed now, and we can proceed with writing it across all the 3 replicas. And again, in those writing as well, 2 of them must be in like in different AGs. And like I said earlier, writes and strongly consistent read always go to the leader. So what happens that the leader appends a write ahead log, like you can say here, WAL and WAL, to each of these their followers. And once it is shipped to the followers, the client acknowledges that, hey, the quorum of peers have now persisted this record. So now the followers can serve the eventual consistent reads, and this split of eventual and consistent is basically a trade-off, but eventual reads can use any replica. Now, one more interesting thing, that not every replica has to, hold the entire B tree. So there is concept of log replica as well that I will explain to you. So what happens that we have a storage replica and we do have a log replica as well. Now, a storage replica has basically the B tree data structure. It is having the full data set on disk. It has the write ahead log, and then it can serve the read request as well. And in order to start this, in case something goes wrong, it will take minutes to start or bootstrap a new storage replica. But there is one more thing called as log replica, and here what actually happens that we only include the recent write ahead log entries. What we do is there is no full data set. So basically there is no B tree at all, and it's only compatible with as a Paxos acceptor role. So all the consensus that needs to be performed, it will perform that, and it cannot serve reads as well. And creating this is really easy because it is getting created in seconds. Okay, so what happens is that even if let's say a particular replication group failed, we can use the log replica to serve the consensus and keep the things going on, and eventually we can make the bootstrap service run again or fix the service by the auto admin. Let's explain this further using an example. So there are, let's say, three nodes, node A, node B, and node C, where node A was the leader and the other two were follower. Now suddenly node B went down. Now what will happen that now the number of because the replica is unresponsive, so what is happening that the number of nodes which can participate in consensus is now down to 2. So what the leader can do is can start or spin up a log replica basically, which will not serve reads but will participating in consensus. So basically the writes can continue while the slower heal of a storage replica will happen in the background. So fast quorum recovery is why the log replicas exist. The paper talks also about an interesting concept in distributed system, which is the lease mechanism, how it works in Amazon DynamoDB. So consider this, that there is one leader and there are two followers. So how will we ensure that the writes are always being handled by only one leader? No other nodes can handle a write operation. So there is this concept of lease. I will explain it further. So let's deep dive into how basically this entire leader of node A will hold the leadership, and it will ensure that there are no two writers at the same point of time. Now, leadership is not a forever title, right? So once elected, once the node A has been confirmed that it is the leader, so a replica can remain leader only while it renews a time-bounded lease. Okay. Now, once this leader has a lease, there is, let's say, 10 seconds. In the paper, there is this example. So a newly elected peer, let's say suddenly from node A, node B now becomes, or node C becomes the new leader. So node C will not serve the, strongly consistent read or write until unless the previous leads gets expired. So once that expires, then only a new member, if it assumes that it is the new leader and it has the lease, then only it can serve the strongly consistent read or write operation. This waiting rule is basically what keeps a single replica allowed to take writes even if election and failure detection or races are happening. The leader basically it keeps sharing the heartbeat to the follower nodes, and then this is how it proves that it is alive, and it keeps renewing its lease. Now, one more interesting thing is the follower who is receiving the heartbeat, what they will do is they will reset their election timers. Okay. And if heartbeat stop, so a replica can, let's say, conclude. We will discuss this again. What will happen that there might be a chance that the leader is gone. So what they will try to elect a new leader. They can even claim themselves propose that I should become the next leader, and we will look into this. So let's say this node A is now down somehow. It didn't send, the leader failed and it didn't hit heartbeat. So followers will still not write because the old lead has not expired. So the lead is still there. So now a peer, let's say node C or node B, they detected that, hey, it might be possible that the leader is down. So what will happen that if the leader is unhealthy or unavailable, they can propose themselves in a new election. But even though if they become the new leader, the B or C, again they need to wait until the previous lease will expire, and once they get it, then only they will start serving the write or strongly consistent read. So basically a newly elected leader will wait till the lease of previous leader expires, and then only they will continue with the operations for write or consistent read. But the write availability, it needs both a healthy leader as well as 2 of 3 quorum across availability zones. So these are some of the requirements which will be always needed. Now, when the lease expires, followers can run multi-paxos to basically elect a new leader, like I said, and any replica can start that round. But the goal is to restore consistent read basically and the write availability as much quickly as possible. So until a new leader is serving, eventually consistent read can still come from any of the remaining, like the B and the C can still serve the eventual consistent read. And the old leader, let's say A, was dead. It's truly dead. Now it no longer holds a validly. So even if comes back alive and then it is thinking that, hey, I am the leader, I will serve the read, then it will won't have the lease to serve it. So it will not be able to take the rights. Now, multi-paxos is basically there, so exactly one replica wins in the entire writing or strong read scenario. So committed data will be still on the surviving replica, right? So once the any particular node goes down, we will have the data still there. But the write will be only acknowledged once the quorum has decided that the log is now persisted. So a healthy write quorum, let's say B has been selected. So a healthy write quorum remains in still the 2 of the 3 replicas that are there in different availability zones. So A and C are still in different availability zones. So even though let's say A went down, B and C were still in different availability zones. So the logs will be persisted there. That is a guarantee. Now the failed node can later on, this A was earlier leader, but now it can later, once it is back up, then it can join later as a follower. And the important invariant is that only one writer will be there. There is no split brain. Okay. No 2 nodes are thinking basically that they are the leader and they will serve the read, like strong read and the write operation. So there are no lost committed entries in our distributed system. And this is really interesting. So let's conclude this. So what will happen that the new leader basically, once it has acquired the lease, so let's say node B acquired the lease, so it will start the heartbeat sending to all the followers. It will accept the rights and request router, basically the service which sends the request. It can the metadata service is there which will update that, hey, this is the new leader for this partition. So the request router can then learn the new location from the metadata service and send the client traffic basically to this particular server. And recovery in that case will be in the order of a couple of seconds, which is really good as compared to the other minutes failure. So once the recovery is done, the partition will be basically back to the same contract, which is there will be one leader, there will be 2 followers, there will be quorum rights, and again strong reads will be served by the leader. All right. Next, what we have coming up here is the architecture or the microservices fleet that I was saying a little bit earlier. But I think this video has already become a bit long. So we can break the video into multiple parts, and then eventually I will release them as separate videos. Thank you so much for watching this video, and it was the journey had just started in this paper, and we are midway currently almost. In the next video, we will be talking about the journey of Amazon DynamoDB from provision to on-demand. We will be talking about how they did the initial improvement to admission control, basically how they were taking requests earlier and what improvement they did, like bursting, and there was adaptive capacity, there was GAC or global admission control. We will talk about all of these in detail in the next video for sure. There are also different splitting concepts, durability, hardware failures, recovery, and everything we will be discussing in the next video. So thanks for watching this video, and just in case, if this video has helped you a little bit even also, and made you a little bit more curious about how these technologies work, I would request you to please subscribe to the channel and help me grow as well. It takes a lot of effort to go through such a detailed research paper in such a detailed way and create so much long videos. It takes a lot of time as well. So yeah, we'll be happy to help any other software engineering mind who is curious enough. And that is all. Thank you so much. And I will see you in the next video at PrepTrain Back the Tech series. Continue with DynamoDB.